Hello and welcome to the Embedded Online Conference. My name is Miro Samek, and in this session I'm going to talk about testing of event-driven embedded software. Specifically, I'll compare the traditional unit testing approach with mocking to the arguably more intuitive and simpler approach based on software tracing. I've been working with the embedded and real-time systems for almost 3 decades now, about half of that time at Quantum Leaps, the company I founded back in 2005. My main interest is in modern embedded software, and I believe that the new approaches to testing are very much part of modernizing embedded software development. Regarding the agenda for today, I will start with a general strategy for testing event-driven software. Next, I'll explain the traditional approach based on the mock objects, and I'll illustrate it with an example. Next, I'll introduce the concept of software tracing, which conceptually is similar to testing with printf, which most of us have applied in one form or another. After this, I will have everything prepared to demonstrate a truly automated testing system based on software tracing and compare it directly with the traditional mocking approach. I'll then show you how the complete system works for a non-trivial hierarchical state machine. And finally, I'll point out some advantages of the software tracing approach compared to the traditional unit testing. Alright, but before jumping into all this, it's probably a good idea to first quickly recall how the traditional unit testing process works for simple stuff. For that, suppose that you wrote a simple function, mystrlen, which returns the length of a zero-terminated string parameter. As usual in unit testing, the code of the test, COT, is located in the src subdirectory and contains the header file with the interface and source file with the implementation. The test code is located in the test subdirectory and is called test.strlen.c. Now, the test code is typically written against the unit testing framework, and here I am using Throw the Switch Unity, which has been specifically designed for testing embedded C. The test code also needs to include a COT interface. The individual tests are just functions in which you first call the COT and then you verify the test assertions. For example, you call your mystrlen function with an empty string argument, and then you verify that the returned length is 0. In the subsequent tests, you can get rid of the temporary len variable, but still the sequence of steps is identical. Finally, in Unity, you need to provide a test runner. You can generate such a runner automatically, but here in this first example, I show how the runner can be written manually. So now let's just see how it works. I open the terminal, change to the test subdirectory, and type make. As usual in the test-driven development, the provided make file both builds the code and immediately runs the tests in one go. As you can see, all tests pass, and so we have a successful run. Alright, so now let's go back to the event-driven embedded systems, which consist of separate event-driven components that communicate by asynchronously posting events to each other. If you are unfamiliar with this architecture, I talked about it in my 2 past presentations at this conference. You can also watch my free videos on YouTube. Once an event is posted, it will eventually be processed to completion on the internal thread of the active object component. The event processing, in general case, involves a state machine, because generally the proper response to an event depends on both the type of the event and the internal state of the system. A state machine handles an event by executing a sequence of actions. For example, an event that triggers a state transition causes an action on the transition, followed by exit action from the source state configuration, followed by entry actions to the target state configuration. The actions themselves typically are function calls to the collaborating passive components, such as device drivers for various peripherals. The bottom line is that the response to a single event consists of the whole sequence of various function calls. And that determines the general testing strategy for such event-driven systems. The testing strategy for event-driven components, which are the natural units for testing, involves injecting events to them and verifying that the component under test executes the expected sequence of function calls. Please note that this approach goes beyond the simple unit testing you saw a minute ago. Simply calling the CUT and then examining the effects won't cut it here, because you are interested in the precise sequence of interactions while the CUT was running to completion, not just one final result. But this problem is, of course, very common, and the unit testing community has devised a generic mechanism to verify the whole sequences of function calls. To explain this mechanism, I've chosen an example originally presented by Matt Chernowski in his video blog post entitled "Test Driving with Mocks Instead of Real Hardware." I highly recommend watching Matt's video because it very well explains the whole traditional process and tools such as Seedling and the Unity framework. And since my goal today is to compare the traditional approach to a new one, I will build on this example. So Matt has come up with an LED bar gizmo consisting of a row of LEDs that collectively visualize a percentage. The main interface to the LED bar gizmo is the LED bar set% function, which internally interacts with the individual LEDs. For example, the function called with the argument equal to 60% should turn 3 leftmost LEDs on and the remaining LEDs off. To test this function, you need to verify that exact sequence of interactions with the LEDs. To do this, you cannot use the actual LED module, because it simply doesn't keep track of any calls made to it. Instead, you can use a test double called mock LED, which will provide a dummy implementation of the LED interface, but it will also store the expected sequence of calls to that interface. Here is the general structure of your unit tests based on the mock LED test double. You will have two interfaces: the led.h header file with prototypes of the LED on and LED off functions, and the ledbar.h header file with the prototype of the LED bar set% function. You will also need the implementation file, ledbar.c, which will obviously use the led.h interface. All these three files will be your code under test, CUT, so they will live in the src subdirectory. Now you will need some code only for testing. Here you will have mock led.h header file, which will extend the led.h interface and provide additional functions just for managing the mock. You will also need the implementation file for the mock called mockled.c. The good news is that both mockled.h and mockled.c can be automatically generated just from the led.h interface. You'll see it in a minute. And finally, you will need to write the tests, which will live in the test ledbar.c implementation file. Please note that for testing, you will not need the actual implementation file, led.c. This is what Matt Chernowski meant by testing without real hardware. This is one of the huge benefits of the mocking approach. Alright, so now let's see how all this actually works. I open the project directory Unity LED bar, and here, first let's take a look at the code under test, CUT, in the src subdirectory. The led.h interface contains the prototypes of the LED on and LED off functions. But to make this example a little more complete compared to Matt Chernowski's version, the LED on function now returns a value, which will demonstrate an important feature for the mocked interface. The returned value in this case will be the power consumption in milliwatts of the particular LED that is being turned on. The main CUT here is the ledbar.c implementation with the LED bar set% function. This function starts with calculating the cutoff index of the last LED that needs to be turned on. Next, you see a precondition asserting that the cutoff index is in range. Next, all LEDs up to the cutoff index are turned on and their power draw is added up. The remaining LEDs are turned off and the function returns the calculated power draw. Regarding the code used only for testing, currently you have here only the test ledbar.c with the actual tests. But before I explain the tests, let's generate the mock. I open the terminal and go to the test subdirectory and run the cmock tool with the argument of the led.h interface that I wish to mock. Here I call cmock explicitly for demonstration, but in a real project you most likely would use something like Seedling to automate that step. As you can see, CMOC generated the mocks subdirectory with the extended mock interface and the mock implementation. To understand the tests, you only need to look at the mock interface, mockled.h, where you can see the included original interface plus macros to program the mock. Now you can finally appreciate the tests. So as before, tests are functions, but this time they don't start with calling the CUT. In fact, the testing steps are now exactly reversed, and the CUT is called last. This is because now you need to program your mock before calling the CUT. So for example, in the very first test LED bar 0% all off, you begin with programming the mock to expect the calls, LED off with argument 0, LED off with argument 1, etc. Only after that, you call the CUT with argument 0%. In the next test LED bar 100% all on, you program the mock to expect the call, LED on with argument 0 and return value of 10. So as you can see, the mock allows you to specify the return value from the expected call. Other tests expect sequences with some combinations of LED on and LED off calls. As before, your tests require a test runner, but this time the runner will be generated automatically based on the tests. I do this manually here for demonstration, but in a real project, you would most likely use something like Seedling to automate that step. Anyway, as you can see, the test runner is now more involved because for every test, it initializes CMOC, calls the setup function, calls the test function, calls the teardown function, verifies the mock, and finally it destroys the mock. So now let's run all this by typing make. Again, the provided makefile builds the code and immediately runs the tests. As you can see, most tests pass, except one where you call the set% function with 200% to test the precondition assertion. In this test, you exactly expect breaking the assertion, so the reported failure is really a false negative, because this test should pass. Unfortunately, there is no mechanism, neither in the mock nor in the standard Unity framework, to specify such an expectation, because normally breaking an assertion means failure. Of course, this can be fixed, and for example, Matt Chernowski has proposed a workaround for testing assertions with the Unity framework. Still, please note that as long as you stick to the traditional unit testing approach, mocking is the primary way of testing event-driven systems, so you will be using this method all the time. In fact, you will mock yourself to death. But let's step back and think fresh about the problem. Suppose for a minute that you are tasked with verifying the sequence of LED function calls produced by the LED bar set% function, but without the whole machinery of mock generators and test runners. How would you go about it? Well, I suppose that most developers would apply the tried and true printf method. Specifically, instead of creating the mock test double, you will come up with a much simpler test double called the spy, where the LED on and LED off functions simply print out that they've been called and which parameters they received. For the return values, you could use a static array of predetermined values like that. Now you need a main function to call set%CUT, but to avoid contaminating the actual production code with printf, you might wrap the call in a trace function like this. Now in main, you simply call the trace function with different parameters, which actually correspond to the tests you just performed with the mock. All this is quite simple and intuitive, so in just a few minutes you would be able to produce the following output. This output contains the exact same information as the original tests with the mock. Of course, at this point you'd have to verify the correctness of this output manually, but this process can be automated, as I'll explain in a minute. But before that, I need to mention that the process of instrumenting the code for the purpose of generating a trace of the code execution is more scientifically called software tracing, sometimes referred to as logging. The use of printf for instrumenting the code is the most primitive software tracing method and is really just about the least appropriate for embedded systems. The main problem with printf, or the related sprintf and similar, are that the computationally expensive formatting to ASCII clogs the time-critical paths through the code. Of course, in embedded systems, the output has to be sent out, typically via a serial interface, and this takes even more time than formatting. Finally, ASCII format is a very wasteful way of sending out information. For these reasons, software tracing systems for embedded code, such as the system called QP-SPI I'm showing here, are typically not based on printf, but rather on a binary format. Typically, chunks of binary data called trace records are stored quickly in a RAM buffer, so the data production and transmission are separated. Typically, the trace data from the buffer is then sent during the idle time, which removes tracing from the time-critical paths and minimizes its intrusiveness. The binary data protocols have provisions for detecting errors, as well as any discontinuities in the data stream. Also, critically important is the ability to quickly resynchronize the receiver to the next data record after any error. Finally, the reception of the binary data in the host computer requires more than a serial terminal. Typically, software tracing systems provide a specialized host application to decompress and visualize the data. For the QP-SPI software tracing system, this host utility is called QSPI, and I'll demonstrate it in a minute. For other software tracing systems, the host application might be called Tracealyzer, System View, Micro-C Trace, etc. So let's actually see how to replace printfs with QP-SPI and how it will work. The code is located in the trace subdirectory, where you have the spy led.c test double and the trace ledbar.c converted to use QP-SPI instead of printf. In spy.led.c, you first see the output of the quote-unquote dictionaries, which provide symbolic information for rendering the traced on the host, similar to the symbolic information that the traditional debugger needs to display your function names and variables. You'll see how it works momentarily. Next, in the LED-off implementation, you see how a trace record is produced. The data packet is delimited by the QSBeginID, QSEnd macros. Inside the record, you see the output of a function data element and U8 data element. In the on implementation, you see a similar trace record structure plus output of the return value as U32 data element. The use of the macros in the tracing instrumentation allows you to deactivate the instrumentation with a single preprocessor switch. Specifically, the tracing instrumentation is typically active only in the SPI build configuration where the macro QSPI is defined. When the macro is not defined, the instrumentation macros are replaced with dummies, so the tracing instrumentation produces no code. All this means that you can leave the tracing instrumentation in the production code. But going back to finishing the conversion from printf to QP-SPI, in the trace ledbar.c module, you can see the trace record inside the trace ledbar % function and some additional initialization of the QP-SPI software tracing system. Otherwise, the tracing calls are identical as before with printf. Now, to build and run this QP-SPI tracing example, I need to change to the trace subdirectory. But before typing make, I need to open a second terminal and launch the special QSPI host application. Only now I can build and run the code by typing make configuration equals SPI. You can see the tracing output in the QSPI terminal. The first part corresponds to the dictionaries produced at the beginning. You can see here the mapping between the binary addresses inside the target and symbolic names. These names are then used in the subsequent trace records. For comparison, I run again the simple printf version. I hope you can see that the outputs match pretty closely. So far, all the examples I showed you ran on the host computer, but software tracing should also, and perhaps first of all, run on the embedded targets. To demonstrate that indeed QP-SPI can do this, I prepared a makefile for the little STM32 Nucleo L0 board with ARM Cortex-M0 Plus CPU. The build process uses obviously a different port of QP-SPI and a different cross-compiler, but the SPI LED.c and trace LED-bar.c modules are exactly the same. The only important difference is that the QSPI host utility now needs to connect to the embedded board, which conveniently provides a virtual COM port. To connect to that port, qspy needs to be called with the -c com4 parameter. After this, you can program the Nucleo board simply by copying the compiled binary onto the USB drive corresponding to the board. As you can see, the embedded board produces identical output as the host executable before. Alright, at this point I have everything prepared for part 2 of the presentation, where I'll introduce a truly automated testing system based on software tracing, called Qtest.